Now we will discuss some interesting phenomena from traveling waves. First, let us discuss coherent waves. So if two or more waves are monochromatic, that is, they have the same wavelength or frequency and they have the same phase also, so they are called coherent waves. So the sources that generate waves that are monochromatic and are in same phase, they are called coherent wave sources. An example is a laser. A laser can generate light waves of one particular wavelength, and all the light waves generated by the laser can be in phase basically. So it is a coherent source of light waves. Now we will describe the phenomena of superposition. So when traveling waves meet, they will interfere with each other. This is called wave interference. And basically what happens is that their positions are added to one another. Each point in the wave basically has some amplitude, and those have to be added together to get the resultant wave that forms. And two interfering waves can form very interesting patterns, as we will see in a few slides from now. So the interference pattern actually depends on the phase of each traveling waves. And there we will look at a couple of interesting cases. For example, let us first look at a case where the interfering waves are in phase. So on the left you see two waves. They have the same phase. They are starting from an angle 0 basically, and they have the same wavelength, same phase. And now if they are interfering, to obtain their resultant wave, you have to add up each of the points along the wave. So if you take the point that is labeled as 0, add them up, this has 0 amplitude. So the resultant wave at this point will also have 0 amplitude. Now if you take the peak amplitude of each point, we see that it is 1 at the peak. Both the waves are 1. So 1 plus 1 gives you 2. And you see the resultant wave has the maximum amplitude of 2 also. So if you just add up each of the points along the wave, the corresponding points, you will end up with the resultant wave. So because the waves are in phase, the resultant wave has a larger amplitude in this case. Now what happens if the waves are out of phase completely? So over here we see two waves that are 180 degree out of phase. When there was basically a positive amplitude, maximum positive amplitude for one of the wave, the other wave has the maximum negative amplitude basically. And so we add up each of the points between these two waves, and we end up with a resultant wave of 0 amplitude. That these waves kind of completely annihilate each other, and we don't get a wave at all, or the wave that we get has 0 amplitude basically. So this is called destructive interference. The previous case was constructive interference, where the two waves are adding up to form a larger wave. In this case, the two waves are kind of destroying each other, and they are called destructive interference. But in general, the waves may not be completely in phase or completely out of phase. They could be somewhere in the middle. There could be a phase offset between the two waves. In this case, this phase offset is shown in this case. One of the waves, they have a slight phase offset compared to the other waves. In this case, you can form some form of pattern in the wave. Basically, again you have to add the two corresponding points in the wave at each position basically, and you end up with a resultant wave. For example, in this case, given by this figure. So another interesting phenomena that can happen when waves meet is the phenomena of standing waves. So standing waves appear to be standing still basically. They don't appear to be propagating. They appear to be almost still basically. And this happens when waves traveling in opposite directions interfere with each other under some boundary conditions, for example. We'll see soon. So for a standing wave to form, the medium needs to be of a fixed length. The waves have to form within a fixed length. So let us look at the mathematical description first. So we have two traveling waves traveling in opposite directions, given by the wave equation we have seen before. So notice the argument of the sign here. One has minus omega t, the other one has positive omega t. So the minus omega t refers to a wave traveling in the positive direction or the right direction in this case, and the plus omega t refers to a wave traveling to the left in this case. So these two waves, what happens if they interfere? So again, remember, we have to add each of the points on the wave. So this is the resultant wave is given by the sum d1 plus d2 in this case, and we obtain something like dm sine kx minus omega t plus dm sine kx plus omega t. And we can simplify this expression further to see the pattern, that the standing wave pattern that is formed. In order to do that, we will make use of this trigonometric identity, sine of theta 1 plus sine of theta 2, and this can be written as 2 times sine of some angle times cosine of some other angle, and the angles are basically theta 1 plus theta 2 over 2, and for the sine, and for the cosine the argument is theta 1 minus theta 2 over 2. Now if we use theta 1 to be kx and theta 2 to be omega t, then we can obtain this expression 2 times dm times sine of kx times cos of omega t. So this is the standing wave pattern that is formed. And notice that in this case, if x is 0, the wave is actually 0. So irrespective of the time, no matter how the time varies, this position 0 always gives an amplitude of 0, a displacement of 0 for the wave. So if a position is at 0, that is not so the x equal to 0 position is never moving along this wave. It's always fixed. But if x has some other value, so that the sine kx is actually a non-zero number, then the amplitude of the wave at that position can vary with time. It will be modulated by cosine omega t. Let us look at some examples, then it will be clear. And this is one of the patterns that we can see. Basically, what we have labeled here is a standing wave pattern with the vertical lines representing the amplitude of oscillation at each point. And notice that the position x equal to 0 has no amplitude associated with it, that is fixed. But the peak amplitude, that has a very large vertical line associated with it, showing that it can oscillate the maximum amount. But as a whole, the wave doesn't appear to be traveling, it is kind of standing in this pattern. And so in general, when two waves interfere in this manner, they form what is called nodes and antinodes. So the nodes are the positions where there is no vertical displacement of the medium. So places where the medium has 0 displacement, these are nodes, as you can see in this figure. And the antinodes are the places where the medium has the maximum displacement. These antinodes oscillate with the highest amplitude between positive and negative signs. What is the effect of varying the frequency when there is a standing wave that forms? So you can think of an example of a standing wave as a rope that is tied to one end, and you are shaking the rope, the other end of the rope with your hand like this. So in this way, you can generate actually standing wave patterns, because you are generating a wave in one direction, and that wave is getting reflected back from the other end of the string that is fixed basically. So these two traveling waves of traveling in opposite directions form a standing wave, and you see patterns that are shown in this figure. So if you are shaking the rope at a very low frequency, then what you see is the standing wave pattern shown in the first figure here, in the top figure, and that is just a half wavelength basically. That's not a full wavelength, that's just lambda over 2. And this is the lowest, this is the first harmonic, it's called the fundamental frequency or the first harmonic of the standing wave. So this happens when the length of the string is equal to half lambda basically. Now now if you start shaking the rope slightly more vigorously, so that you are shaking the rope with a higher frequency, you see that there is a second harmonic that develops. In this case, the standing wave patterns has two lobes with nodes at both ends, and there is a node at the middle, basically, with no node at one end, and there is a node at the middle. And there are antinodes. There are two antinodes as seen. So this is a full wavelength lambda, and so in this case, the length of the rope is equal to the wavelength. Then if you start shaking the rope more vigorously, you increase the frequency, and you see even higher harmonics. The next one is the third harmonic, or also called the second overtone, and this is equal to 3/2 of the wavelength, lambda 3 basically. You can see that there are a number of nodes, 3 nodes forming and 3 antinodes forming. The number of nodes and antinodes, they are directly related to the harmonics of the wave. So in the last example, we kept the length of the rope fixed. Now let us try to change the length of the system and see what happens. And we will take a look at the example of an air column. This is shown in this figure. This example shows an air column that is open at one end and filled with fluid from the bottom. So there is a small space that is left above the fluid. And so this can, because of traveling waves of air molecules, basically, traveling waves of sound, basically, can come and reflect back from the surface and form standing wave patterns. And then the number of wavelengths that can, or the number of the harmonics will actually depend on the length of this air column, basically. So if you reduce the volume of the fluid, like if you put less fluid in this column or the tube, then you can observe higher harmonics of the system, as shown here. So what do the speed of the waves depend on? So in air, the speed of a wave is given as the bulk square root of the bulk modulus divided by the density. This is the density of the air and the bulk modulus of the air, that is pressure. Pressure is given as Newton per meter square, that is force per unit area. So if the pressure is more, that is the force per unit area is more, then the speed is more. So if the air is compressed with a larger force, then the speed will be larger. And if the medium is more massive, such as the density is larger, then actually the speed decreases, because there is an extra inertia associated with the molecules that go vibrations. And what is the expression of the speed for in a wire, speed of the wave in a wire under tension? So when I am applying a force to the air, I am exerting a tension to the wire, newtons. So the speed is given by the square root of tension over mu. Mu is the linear density of the rope, basically, how dense the rope is. And again, the more the force or the tension, the more the speed. And the denser the rope is, the harder it is to move. Basically, there's some sort of inertia. So it's harder for the wave to travel. So the speed is less, actually, if the rope is denser. Now let us summarize the last discussion, basically, because there were a number of variables and equations. So we defined a lot of terms. So let us just summarize all the variables and the wave equation, because it will be very important in your future studies. So the wave equation is of this form: displacement as a function of position and time, and dm, there is a dm associated with it, and there's a sinusoidal, you can write it as a sine wave. The argument of the sine is kx plus minus omega t plus phi. Plus represents a wave traveling to the left, and minus represents a wave traveling to the right. So what are the variables? So we define the phase. The phase is just the argument of this sinusoidal wave, kx plus minus omega t plus phi. And then phi is called the phase offset. This is basically an angle at the starting point, how two waves are different basically. That angle is given by this phi variable. And then there's a wavelength associated with it, lambda in this case. It is hidden inside the wave number k. There is a period associated with the wave, it's called t. We have defined the wave number k as 2 pi over lambda. We have also defined angular frequency, which is related to the actual frequency through the relationship omega equals 2 pi f. And we have also discussed the phase velocity, which is given by lambda times f, which is also equal to omega over k.